I would like to begin this academic program. The first talk will be by Professor Chidambaram, and I invite him to the stage to deliver the talk.
Pleasure to be here. We just now heard from Dr. Ravindran the achievements of the Institute of Mathematical Sciences. And as I said before, IMSC is a leader in mathematics, not just in India, but in the world. We have had some excellent mathematicians who have been faculty members here. And of course, it's obvious that most all sciences require mathematics. And that's why I thought I'll talk to you today about the importance of mathematics to other sciences. Talking more generally, the India of our dreams, particularly the young fellows, young people in the audience, is an India which is economically developed, where the Human Development Index is high, which is scientifically advanced, and with a knowledge economy. A knowledge economy is an economy with the ability to generate new knowledge and with the ability to appropriate knowledge generated anywhere in the world with the idea of deriving value from it. And the India of our dreams, particularly the scientists, is a research development innovation ecosystem with excellence in basic research, including what I have called directed basic research, not directed by anybody, but directed by India's needs, not applied research, but basic research whose value will be derived using technology foresight, selecting the fields in the longer run. Applied research, of course, technology development, R&D led innovation backed by high quality manufacturing skills. We also want an India which is militarily strong. Uniquely, we are an economically developing country where parts of the S&T system are highly developed. Of course, this institute itself is an example. We are developed in some areas of defense, knowledge chemicals, and so on. We also need an appetite for risk-taking. Phil Rosenweis is excellent in the book. It's an excellent book in which Phil Rosenweis has written an article. He says when it comes to technological breakthroughs or launching new products, it is better to act and fail than fail to act. This is also true of research. When you are taking up different areas in research, it is better to start and fail than not start that program at all. And we all know that you never fully fail. From there, some other new ideas and come. Of course, the contrary is to do what is called safe research. You know it will work. You can also get it published in good journals. But is it important? As Peter Medawar has asked, always work on important problems. Important to science or important to society. Nobel laureate Abhijit Banerjee, of course he is an economist, he says, he's talking of economics, poor people take up low risk, low return projects because they fear the risk. So they remain poor. So you can paraphrase it for research. People who want to play safe, take up safe projects, and that rest of it you can make up. And of course we want leaders. As you all know, India celebrates 4 days in science and technology. Science Day, the day the discovery of the effect named after him was announced by C.V. Raman. Of course, he was the greatest experimental physicist India has produced. Mathematics Day, birthday of Srinivasa Ramanujan. Engineers Day, birthday of Mokshagundam Vishweshwaraya, greatest civil engineer India has produced. Then, of course, Technology Day, the first day of the Pokhran test. C.V. Raman, when he got the Nobel Prize, this is in Vigyan Prasar Science Portal. See, he told, when the Nobel was awarded to announce, I saw it as a personal triumph, an achievement for me and my collaborators. But when I sat in that crowded hall and I saw the sea of Western faces surrounding me, and I, the only Indian, in my turban and closed coat, it dawned on me that I was really representing my people and my country. I felt truly humble when I received the prize from King Gustav. Then I turned around and saw the British Union Jack under which I had been sitting, and it was then that I realized that my poor country, India, did not even have a flag of her own. And it was this that triggered off my complete breakdown. See, when I was a student in the Indian Institute of Science, Raman Institute was near me, and I have seen him, and he was a very tough, strong man. Very difficult to imagine C.V. Raman breaking down, but it happened here. Of course, today, 75 years after independence, the young people have huge opportunities and they should make full use of it. This is, of course, Srinivas Ramanujan, and all the mathematicians know. And Srinivas Rao, is he in the audience by any chance? You are, sorry, I almost recognized you. But, but I was not sure. But he's written a beautiful book on Srinivas Ramanujan, life and work of a natural mathematical genius. Right. Show it to the audience. Yes. See, this is a quote from this book. The natural mathematical genius born in an orthodox Iyengar family is an enigma, the Big Bang, and is a Swayambhu. Many good things in the book, nice books, but this I selected what I like the best. In a short lifespan of 32 years, 4 months, 4 days, he has left behind the famous notebooks containing about 4,000 theorems, which set the mind of Cambridge mathematician Professor G.H. Hardy wonder with awe and admiration, for there were no mistakes at all. The fact that Ramanujan knew but did not write down the proofs of his theorems in his notebooks continues to be a boon to generations of great mathematicians like George Andrews, in fact, who was a discoverer of the lost notebook of Ramanujan in 1976. There was centenary 1987, 125th birth anniversary. Celebrated here, no? That was celebrated in math science. And of course, it has applications which Ramanujan would have never have imagined in cryptography and coding theory as well. Nobel laureate Chandrasekhar said, as long as people do mathematics, the work of Ramanujan will continue to be appreciated. Of course, just now we heard a detailed description from Dr. Ravindran, but if I classify it very broadly, theoretical physics, mathematics, theoretical computer science, and computational biology gives you an idea of the range of application of mathematics in various areas. Roger Bacon, Bacon is a favorite quotation for me. Mathematics is the door and the key to the sciences. And you look when Bacon lived. COVID was briefly mentioned by Dr. Amindran, and of course it has been modeled, mathematically modeled, to study the disease dynamics, disease spreading. This is an area in which IMSC has interest, and develop prevention strategies against the spreading. The influential parameters are identified and the proper prevention strategies, including lockdowns, are developed. Such modeling has been also done for COVID-19 pandemic. It's also attempt to predict it's quite a good work in IIT Kanpur also, and also speculate on whether there would be a next wave, and if so, when. See, the second half of the 20th century has seen the emergence in parallel with the advent of computers of ever increasing power, or what is referred to as computational science. And the essence of computational science is the development of algorithms based on mathematical models and their use in simulation. We do that even in condensed matter physics in a very large way. Mathematics is the foundation on which computer science is built, as you all know. But computing is also increasingly used as a key component in mathematical problem solving, because computational mathematics. There are theory-driven experiments, and experiment-driven theories also are there. Take the Higgs boson, for instance. The weak force and the electromagnetic force can be described with the same theory. This is the famous standard model of physics. And the only particle they could not see was the Higgs boson. And E is equal to mc squared. Energy disappears, mass disappears, you get energy. That's how the entire nuclear power program is built. But if energy disappears, mass has to be produced. If you read E is equal to mc squared the other way, and they knew the mass of the Higgs boson, 120, 130, 150 times the mass of the hadron, that's the proton. So you needed collisions at least at 4 tera electron volt for a new mass particle like that to be produced. That's what happened in the Large Hadron Collider. And India has, by the way, that was done during my time. See, I have always said India, maybe it's somewhere else in that slide, India is no longer a small in science country. So we should go for international collaboration, but always on an equal partner basis. And the whole thing happened when I was chairing the Board of Governors in IAEA, and one of the Western country guys, and he says, we are suffering from donor fatigue, as though they have been feeding so much to the developing countries. Now they are suffering from fatigue. That's the day I decided that the Department of Atomic Energy will never go for international collaboration on a donor-recipient basis, but only on an equal partner basis. That's how you see in the Large Hadron Collider. It's a 26-kilometer circumference tunnel, 100 meters below the ground. Hadrons, that is, protons are moving in opposite directions. Once in a while, they collide, energy disappears, mass is produced. And they knew, predicting the mass of the Higgs boson, that they must go to at least 4 tera electron volt before you can see this. And hadron, proton, charged particle can be bent by dipole magnet, but it has to be focused by corrector magnets. And in that 26 kilometers circle, 1,800 of the corrector magnet, sextupole, octupole, decapole were supplied by India. At $40 million worth of equipment was supplied by India. So a big place. The same thing with ITER, to which we have contributed very significantly. Of course, theoretically, we have participated. C.P. Vishweshwara, RRI, and Sanjeev Dhoranda, Ayuka. And in this predicting the existence of gravitational waves, and then the LIGO facility. Experimental driven theory is superconductivity. First superconductivity was discovered, then a lot of theories has been developed, Badin-Cooper-Shepard theory, and now Professor Hiroyashi Koizumi has come up with a new theory using the mathematical tool. I will not go into the details. All this involves very high level mathematics to understand what is a very important physical phenomenon. Artificial intelligence and mathematics, you can't have artificial intelligence without mathematics. And the three areas which are used there are linear algebra, calculus, and probability. The relevance applications in AI include vectors, matrices, eigenvalues, eigenvectors, and calculus functions, vector, matrix calculation, probability-based theorem to calculate the next step of the robot when the already executed step is given. Then you need the Bayes theorem. And other areas that may be needed in AI include information theory, Markov chain, stochastic process used for reinforcement learning. That's not just one-time learning, but you can go on reinforcing the links as compared to supervised machine learning. You can continue to teach it or it learns by itself. Future, AI and ML are omnipresent. Everywhere people are using, we used it, for example, in designing expert systems. 2015, when I was at PSA, we had funded this project in order to be able to predict flooding in cities, flood control. Of course, institution here was involved. Of course, there is a reducing human-machine divide. See, robotics is a part of artificial intelligence. And then many people who are scared, including Professor Stephen Hawking, that one day AI systems may take over the world. I don't agree. I agree more with people like Roger Penrose and some other leading scientists who argue. They use the Gödel's incompleteness theorem to show that any cybernetic system or algorithm developed by man cannot be smarter than the man himself. I agree with that. I think it's pretty obvious to me. Of course, there are super intelligent robots, from artificial intelligence to robots to super intelligent robots. And this is a review of the book on the man who knew infinity, about Ramanujan. And this Isaac Drawer says this is a fascinating book as recognized by many reviews, but I suggest a different perspective. Namely, the challenge posed by the mind of Srinivasa Ramanujan to the idea of super intelligent robots. Ramanujan was a super genius whose theorems, with novel ideas from his handwritten books, would, at intellectually back-breaking cost, be proved to, yet leave mathematicians baffled that anyone could have divined them in the first place. You see his statue in the entrance to Math Science. This brings me to the current efforts to spawn robots with artificial general intelligence and beyond, robots with super intelligence. And he concludes, no enhancement of human intelligence opens a door to becoming a Ramanujan, and no algorithm is likely to produce robots with intelligence, with the abilities of Ramanujan. Mathematics in cyber security. See, internet is very convenient. The more you connect, the more convenient it is. But the more you connect, the more insecure you become. So you have to defend the internet. And it's a difficult and continuously evolving exercise. You know the story of two young girls playing even or odd. That this girl has kept even. Next time she knows she will keep odd. But if this girl is smarter than that girl, she would know that she is expecting odd after even, I'll keep even after odd. But if this girl is smarter than this girl, she would have worked out. But if this girl is smart, there is a never-ending series here. In a similar way, cyber attacker and the cyber defender. This is a battle which is unending, which will never end, because everyone tries to be smarter than the other. And mathematics plays a key role in both preventing and modeling security breaches, with many cyber security tools and algorithms based actually on mathematical ideas. Take cryptography. Encryption is based on mathematical theory, includes random number generation, which is a very big part of that. And the possible advent of quantum computers in the coming decade, because none is available now, maybe they will come in the next 10 years. It can break any RSA code. Once a quantum computer comes, it's so powerful, it can break any one of these RSA, Rivers, Shamira, Adelman code. And then that's why this field is developing post-quantum cryptography. Once the quantum computer goes, how will you have encrypt information which cannot even be broken by quantum computers? And the sets here, as I told you, which is very close to math science, they are working in this field of post-quantum cryptography. Of course, mathematical statistics, the great man, P.C. Mahalanobis, pioneer in this field of statistical science. In fact, I had gone for his 120th birth anniversary. And India's large-scale economic sample surveys carry credibility today only because of P.C. Mahalanobis. And he established, as you know, the Indian Statistical Institute, but which had started in Presidency College, the statistical lab, and there have been top-class experts in statistical science followed, like Dr. C.R. Rao. Game theory and economics is from a book by Professor Y. Narahari, Institute of Science. He's written a very book. Opposite of game theory is mechanism design. So, and study of strategic interactions among rational decision makers. It is connected to situations where decisions interact, where the payoff for a decision maker depends not only on his or own decision, but also on the decisions of others, which is what happens in normal life. And game theory has been widely recognized, important tool in many fields, particularly economics. John Nash, the American mathematician, is awarded the 1994 Nobel Prize for economics for his landmark work on the mathematics of game theory. So far, Nobel Prize in economics has been won, you may be surprised by this, by 11 game theorists, because game theory has entered economics in such a, this is a quote from Professor Narahari, has written an authoritative book on this subject. Of course, Nobel laureates Abhijit Banerjee and his wife Esther Duflo, who got the Nobel Prize with him, Duflo, and have said that the lack of empirical evidence to back theoretical predictions has affected the credibility of economics. And the Nobel Prize in Economics 2021 has been given to a trio for their work in empirical economics, not just theoretical predictive economics. Biomathematics, use of mathematical models to understand phenomena, many areas of biology, physical biology, immunology, evolution, conservation biology. And the results obtained using model simulation are used to test and extend biological theories, such as new experiments. And then we have computational biology, which included bioinformatics. Of course, there is also biophysics. And the pioneer in this was Professor G.N. Ramchandran, who was next door to both CLRI and Institute of Mathematical Sciences. Famous for his work on collagen. You know, they got the Nobel Prize for solving the double helix structure of DNA. But collagen is a triple helix and Ramachandran solved it. If you had access to that data, which unfortunately didn't have, I think you would have done it much more easily than solving a double helical structure. Of course, he was a web pioneer in this field, and when we were students, we used to go and hear his lectures, and that of Alladi Ramakrishna used to come from Presidency College for the lectures that were being suggested by him. And biomathematics use tools like real and complex analysis, integral and differential systems, algebra, geometry, number theory, topology. It's a very use is in biomathematics, because biological systems are complex systems. And of course, computational biology. Data science has become very popular now in molecular biology, particularly genomics. Let me conclude by something I have been always fascinated by, the mathematics in nature around us, mostly through symmetry. We are symmetric. There are symmetries here in the human body. Many organisms have that. Microscopic organisms, humans have bilateral symmetry. Distinct and specific reasons why organisms have specific symmetries. Of course, there are so many examples, but I was starfish. It has rotational symmetry. So it can attack a prey from all directions. How nature has created that. Number of petals on a flower follow the Fibonacci sequence. And so many others do. Fractals. Fractals is a non-regular geometric shape that has the same degree of non-regularity on all scales. Fractals are fascinating. Makeup for branching of neurons in our brain is decided by fractals. Bees build their hives using a tessellation of hexagons, because hexagons cover space very nicely. Concentric circles, a common example is the ripple of a pond. You put it, ripples go. All this is mathematics in nature, which is right in front of our eyes. But we also see concentric circles in the layers of an onion. See, it's all concentric circles. And rings of trees that form as it grows. If you cut it, you can see. Shape of our galaxy is a Fibonacci spiral. Planets orbit the sun on paths that are concentric. We also see concentric circles in the rings of Saturn. We also see unique symmetry in outer space, that is the symmetry between Earth, Moon and Sun. That's what makes a solar eclipse possible. So nature has used all these mathematics in its own way. So I think I'm going to close with another famous quotation by Eugene Paul Wigner. The language of mathematics reveals itself to be unreasonably effective in the natural sciences. So kind of mathematics is omnipresent, whatever kind of scientist you are. So thank you very much. So I enjoyed being with you.
For this wonderful presentation. And it is also honor for us to actually present to you a small gift.